So, hi everyone. The topic of my talk is low-resource morphological generation with neural sequence-to-sequence models. And it's basically my PhD work together with my advisor and something with Ryan Cotterell. Okay, that's the overview. So, introduction, conclusion, and I will present 4 papers. And obviously start with the introduction. So, very basic question, what is morphology? Morphology is the study of the internal structure of words. So it's about how word forms change depending on meaning and how words can be decomposed into like smaller meaning-bearing units, the morphemes. Let's look at an example. So here we have a word that's a lemma, that's wash. So you cannot usefully decompose this into anything. Like no character subsequence would mean something that's referred to in the context of like wash. Now you can change this, you can append something, an ed, and here you have a new meaning, which is washed, so the past tense form. You can change this again, so here you add brain, and you have a new meaning again, so this is now brainwashed. And you change it again, and you have unbrainwashed. So this is what morphology is about. Now look at something else. So here if we take wash out, we have something that's obviously not a valid word, so it's unbrain something ed. And even though we don't actually have a word, you're still able to know that the meaning has something to do with like a negation, a brain, and it's somehow probably a past tense word. Okay, something else. So this word is Donau-Dampfschifffahrtsgesellschaftskapitän. That's a totally valid word in German, even though you'd probably never ever use this in a conversation because it's just not something normal people talk about. The meaning can be decomposed into the following. So we have this one, this is a river. Then Dampf means steam and Schiff means boat. So this is like a steamboat on this river. Then Fahrt means drive and there's an S connecting the words. Gesellschafts is basically consists of Gesell, which is like has a meaning of social. Schaft usually is used to build a noun in German and S is again to connect it. And then we have Kapitän, which is captain. So this whole thing would be like the captain of a society of a drive on a steamboat somewhere. So this is why you would probably not use this. But yeah, so this is how morphology works. So let's look at some definitions that will be used during this talk. A lemma in general is the citation form or base form of a word. So if you want to look something up in a dictionary, you would not try to find a Donau-Dampfschifffahrtsgesellschafts and so on. Here, for example, the lemma would be brain or wash, or drive or boat. And inflected forms of a word are the surface forms of a lemma. So those are forms you would usually find in the context of a sentence. Examples would be like washed, brains, washing, or washes. Then morphemes are the smallest meaning-bearing units of a word. So in the examples before, brain, wash, ed, or drive, or like those parts. So those are basically the ones that are not, that you cannot split up anymore. And a paradigm is the set of all inflected forms of a lemma. So the lemma wash would have the forms wash, washes, washing, and washed. In English, verbs usually have like 4 or 5 forms. So for example, if you have eat, you would have 5 forms because you have eat, ate. No, you don't have 4. Eat, ate. You have eaten, eats, and whatever, but there are 5 forms. Then morphology has different parts. So there's inflection in morphology, which is concerned with the creation of word forms. So you could see this as creating all forms of a paradigm. For example, would be boat to boats or wash to washes. Then there's derivation in morphology, which is a bit different in that instead of creating forms from the same paradigm, you create new lemmas. And this comes often, but not necessarily, with a change in part of speech. So if you have drive, as in like the verb to drive, you could have driver. But it could also be something like friend to friendship or to friendly or befriend. Yeah, so this is about derivation. So this is a bit more open than inflection in morphology. And then there's compounding, which would be like you have steam and boat. You can produce something like steamboat. And in English, this is kind of a bit limited. So in German, you can build like very long compounds. Okay, so here's an example for an English nominal paradigm that consists of 2 forms. So in English, you have usually the singular form and the plural form. This is why sometimes people are saying that English is morphologically poor language, because when you just look at the inflection, usually there are not so many forms per paradigm. If you look at a German nominal paradigm, it has 8 forms. So depending on the function in the sentence, you would use like the nominative, genitive, dative forms. So no, there are 8 slots, and some of the forms are the same, but in general, so that's it. And then those paradigms can be differently big in different languages and different part of speech. So verbal paradigms in European languages are usually bigger. Like the Polish verbal paradigm has like 100 forms. There are languages which have paradigms of like several hundred forms. So this can get quite complicated. So now the question is, okay, we're here. Some of us are doing NLP, and why should we care about morphology? I have some examples that are a bit probably simplified. So one is about machine translation. So you need morphology to accurately understand sentences in many cases. If you have this sentence, which is, isst gerne Apfelkuchenstücke, you have basically no chance that you will ever find Apfelkuchenstücke in a dictionary, because it's not like a very common thing that would probably be in there. So if you want to translate this, it means he likes to eat unknown, like something. So basically, if you get this out of your translation, you can't really do anything with it. But then if you can split this up and you can produce the right lemmas, then you can have isst gerne Apfel and Kuchen and Stück, and you can look them up separately, and then you would correctly translate this to he likes to eat pieces of apple pie. Then there's the other component. So this one is about understanding. Then it's also important for generation. So imagine you have a language model, you want to produce some text, can be like also for translation, for example. But if you have something like all grown-ups is one's children, you would probably not be very happy with that. You would also not be very happy if you produce all grown-up were one's children. And you would also not be very happy with all grown-ups were one's child. So what you want to produce here would be all grown-ups were one's children. So this is where you also need morphology for generation. Okay, so we're going to look at different tasks. One task we look at is morphological inflection, which consists of you have given a lemma and a target tag, and you want to produce a target inflected form. So for example, you have given eat, and you want to produce the third person singular, they want to produce eats. Or here's another example for German. If you have Schneemann, and you want to produce the dative plural form, you want to produce Schneemännern. Then there's another task which is highly similar, which is morphological reinflection, which consists of, instead of having given the lemma, you have any inflected form from a paradigm together with a target tag, and you want to produce another inflected form. So an example would be this one. So instead of Schneemann, now you have given Schneemännern, and you want to produce Schneemannes. So this is more complicated than morphological inflection in the sense of that you have more combinations. So if the paradigm consists of 8 different slots, for inflection, you have 8 different combinations you would need to kind of cover. If you have reinflection and the paradigm consists of 8 forms, you have 8 by 8, or 8 by 7, so 56 different combinations that you would need to have. And this is important for 2 reasons. If you want to train models and you cannot basically combine this, you want to produce one model for each combination, you need to have this amount of models. And also, if you want to train something, you need to have training data for all possible combinations. So yeah, this one is just more complex. And yeah, so morphological inflection is a special case of reinflection. Then there's another task, paradigm completion. And okay, usually paradigm completion can be used or was used in many papers like a synonym for inflection or reinflection. But here I kind of want to split it a bit and say that paradigm completion is always you have given potentially several forms from a paradigm, and you want to complete the whole paradigm. So you want to produce all missing forms and not just one indicated one. So the task would look like this. So here you have given 4 forms, and you want to produce the missing, fill the missing 4 slots. Okay, so now the question would be, why is this difficult? So one reason would be there are different inflectional classes. So if you have a German word Mund and you want to produce the plural form, you produce Münder. However, if you have Hund, which is super similar, you don't want to produce Hünder, because that's wrong. You want to produce Hunde. Then there are stem changes. So for example, for Spanish, for the word aburrir, you don't want to, or you want to produce, when you want to produce the first person singular present tense, it's aburro. However, if you have the word dormir, then the form that you want to produce is not dormo, the form you want to have is duermo. Okay, so this like kind of differs a bit. And then the irregular inflections. So for example, in English, if you have walk and you want to produce the past tense, you want to produce walked. But if you have eat, you don't want to produce eated, you want to produce ate. And if you have go, you want to produce the respective form here. Okay, so that was the introduction to morphology, and now I'm going to talk about the first part of what I actually did for that, which is encoder-decoder models for generation. And the questions we tried to answer here was, which model can we train well for the reinflection task? And this was done for the SigmaFont 2016 shared task, which basically, so the task was basically just reinflect a lot of words in a lot of languages. So ideally, we didn't want to have one model per language, so we wanted to try to get something that's language independent. And then you could think like, how would you want to do this? Could be character-based, morpheme-based, word-based. Yeah, so that's all the stuff that's going to be answered now, hopefully. And this was work that was with my advisor, and we presented that at ACL 2016. So, okay, how we approached this was, we saw, okay, we have an input word, we have an output word. So you can see this either as words, or you could see both of them as a sequence of characters. So this is like the sequence, S, C, H, and so on. So this is effectively a sequence-to-sequence task. And so we want to use a sequence-to-sequence model for that. Okay, just skip one. So this is basically the model we wanted to apply because it was pretty cool at the time. So an attention-based neural encoder-decoder, actually, it's still cool. So the pipeline for this would be you have the characters of the input word, which you represent as vectors. And then you want to use some type of model to like encode this into a hidden representation and then decode it and get a sequence of output characters. So this is the model that was invented 2015 by Badanau and his colleagues for machine translation. And how this was, basically the original idea was you have a sentence, which is a sequence of words, and you produce another sentence in another language, which is a sequence of words. And instead we applied this to a sequence of characters to sequence of characters. So basically this model consists of mainly two parts. So the lower part, like below the circle, is an RNN, so a recurrent neural network, and the upper part is also a recurrent neural network, which is why I will shortly talk about recurrent neural networks. So this is basically a neural model which is good for input sequences of variable length. So as for words, because of course the words, they have different lengths, like naturally. It uses the same model parameters in each time step and keeps a history of the previous input. So this is how a general RNN would look like. So on the left you have the input layer, then in the middle the hidden layer, and on the right is the output layer. Basically, if you had no sequence but just one single input, it would be the upper line. So you have an input, you kind of encode it, and then you can get some output out of that. And then going down is like so basically the word would be like the upper, second, third characters, and the hidden layer keeps some type of information about the current state at each like character step. So so we have an input, which is a sequence of vectors. And then the hidden layer is basically a nonlinearity applied to like the weighted input and the weighted hidden state. And then for a general RNN, you can have different types of output. So you could basically get one output per input. Then you could apply like a softmax function to like the each hidden layer at each time step, or you can take like the last one and then get the final classification over that. If you, for example, if you have a sentence, you just want to say if it's positive, negative, you could apply this. Just take like the last hidden state, which is like effectively representation of the sentence, and then like classify it. Okay, so that's the general RNN, but the general RNN has kind of a problem with handling long sequences. So because the hidden state gets basically changed at every time step. So if you have a long sequence, at the end you have more information about the last part than about the first part. So imagine you have the sentence, which is like pretty long. It's some part, I think it's like the first sentence from Lord of the Rings. So for your model, it would basically look like that. So the first part is like really unclear, and the last part is like much stronger. And in order to overcome this, there were invented two extensions. So long short-term memory, LSTM, and gated recurrent unit, GRU. And the model we used implements the GRU version for that. So it's basically like that. So the GRU has two gates. So effectively, you have to imagine it's an RNN, but it has some way of deciding at each step which information it wants to keep and which information it wants to throw away and update. And then the hidden state is like that, so it's a bit more complicated. So now what the final model is, now we know the lower part is an RNN, the upper part is also an RNN. And in particular now we're talking about the lower part, which is called the encoder. So we have an embedding layer. So this is basically just the same input as before for the RNN. So one vector per character. And then we apply the gated recurrent unit. And we apply two of them. So if we have an input word like this, we have one network that goes from left to right over it, one that goes from right to left. And the final hidden states is a concatenation of the forward and backward RNN. Then there's the decoder, which is a conditioned character language model. So it basically learns which character sequences are kind of famous in the language. And it's also conditioned, so it produces something that has something to do with the input, and it's not just like a random character sequence in the language. And it predicts the output, so at each time step, the character, which is most likely given the last character state, and basically all the hidden representation of the encoder. Then it also has an attention mechanism, which basically means what I said before about the RNN. You could just take the last state and give it as input like to the next part, but the attention mechanism kind of makes this easier in that you don't need to limit the model to like one vector, but instead the decoder can have access to all hidden states. And it's effectively like weighting the input and taking at each time step the hidden states which are most relevant. Okay, so so the attention mechanism basically makes, this is the circle in the middle, that's a time-dependent context vector with attention weights that are calculated like this. Okay, so now the model part is kind of over. So the idea is basically, in general, we have an input sequence, output sequence. So now what we did, like the main part of our work here was that instead of just encoding the input word and decoding the output word, we encoded the input word together with the source and the target tag. So our final input would look like this. So we have the characters, use the application language, all subtags like a source or target tag, and the start and end symbol. So the input representation is basically some amount of source tags, some amount of target tags, and some amount of characters which build the input word. The output is characters building the output word. So this would be an example. So here you want to reduce the third person singular present tense of tying, which is ties. And this is important because it's effectively multitask training on all tag-to-tag combinations. So what I was saying before, basically about if you have like those combinations of source and target tag, and you would have 64 of them here, like using this representation, you just need to use one single model and you can train it on all data together, which also means that per combination, you need less training data. So that's basically the key thing. That's like multitask training. Okay, so we performed different experiments. One was on the German part of CLX and on 4 pairs of source and target tag that were used by previous work. And the train def test splits were like this, so 500, 1,000, and 1,000 per pair. And because it's 4 pairs, and as we said, we train on everything together, we train on 2,000 instances. The results were basically more or less comparable to the previous state of the art, which was good, but not the main part we were focusing on. But it was also always better than training one model per tag combination. So this was basically what we wanted to achieve. And what is important here is that this is effectively a high resource setting. I mean, it doesn't sound so much to say we have 2,000 examples, but this is only 4 pairs. So imagine your paradigm has 12 forms, then in order to like have the same setting, you would need to have 12 by 12 by 500, so 72,000 training examples. And if the paradigm is bigger, then it would be respectively more. Then we did an experiment showing more the strength of the model, which was on the task 2 of the SigmaFont 2016 shared task. So this was reinflection. And this one had a very large number of pairs of source and target tag. So basically all combinations that were possible in the language. Some of those had very low frequency, so some of those appeared like 3 times. and the experiments were on 8 languages. So, and the train and def splits were like this, so about 13,000 and 1,600. So those were the results we got here. So the baseline is the official baseline of the shared task, which did like pretty well for like Georgian, German, Russian, Spanish, and not so good like for the other ones. And then MET is our model, and the 2 results. So the average is we trained 5 models and basically got the average accuracy, and ensemble would be we let them vote. So we choose the one that most models would predict as correct. And yeah, we basically got very high improvements here. So like 30% for some of the languages, 40 for Turkish. Yeah, so this was basically like the strength of the model, because it's kind of a really like a low resource setting, not like the CLX one. Yeah, and to see, so those languages kind of differ in their properties. So Finnish, Georgian, German, Russian, Spanish, and Turkish are suffixing. Georgian and Navajo are prefixing, and Arabic is a templatic language. Okay, then we did some analysis on how the multitask training helps. So we reduced the training data for one of the 4 tags with CLX. Sure.
Sorry, can you actually explain what those columns were on the last slide again? So baseline was, so relative to the sequence model that trained on all of the data together. That baseline column, or so what is the model represent?
So baseline is the official baseline of the shared task. So that's a non-neural model.
And then
so
the ensemble is not ensembling the baseline with your model.
No. That's because basically, I mean, the neural models, they don't really optimize like a global optimum, right? So like we just like train 5 with like different initialization and then like ensemble them.
So the average model, that shows us like the average performance, but that doesn't give one output. So that's not really something. Is that true? Right? So the average column just gives you a sense of how good it would be?
No, the average is basically just to see what you could expect, right? So like you have 5, and so the average is kind of like, it could be that it's a bit better, a bit worse, but like more or less.
But then you took that actual outputs from those that you were averaging, and you made a single model that actually takes one answer, and that's the ensemble.
Yes, just that it was a very simple solution, so we did not actually make one model. We had those 5 models, and then just voted, like majority voting. Okay, so here we basically reduced for one tag the training examples. So the idea here is to see if you have one tag combination with like very little data, how well could the model perform using the data from the other tag combinations. So the very right point is using 36 training examples for the tag we evaluate on. And the model, which is just trained on 36, basically has like a low, close to 0 accuracy, and our model has still like about 90. So this is basically like where the effect comes in, right? So you can have one thing with very little training data and it still kind of works because it has the other information. Yeah, so here this is kind of the same, reducing the training data for all tag pairs. And then of course it's less, so this is like for the model that's trained on all, it's about 130 training examples, and accuracy is about 25%. But it's still better than the 0 of the other model. Okay, so this was the first part. So about the second part. Now we thought about, okay, this kind of works if you have enough training data, but for example, the last thing we've seen with like the 130 examples, that works still like not really good. So we thought, what else can we do? And the idea was, if we don't have enough training data, we can probably just use training data from another language in order to improve that. Yeah, so this was work together with Ryan and my advisor. And cross-lingual transfer in NLP is actually kind of common. So it has been used for parsing, it has been used for machine translation, named entity recognition, and like a very kind of straightforward way to do cross-lingual transfer would be you have training data in 2 different languages, and they take the one that has like more resources and translate it, or translate the other one and train on that one. However, this is kind of based on the idea that languages express the same things. So like a named entity in one language will still be the same named entity in another language, probably just like named differently. So this is kind of different from morphological inflection because it's not a semantic task, but it's like very language specific. So in fact, it's not so much about the meaning in this setting, it's more about like, it's just a sequence of characters, right? So like, yeah. And so we kind of thought that it might be possible that cross-lingual transfer if it works, would only work for like really related languages. Okay, now to see this from the other point of view, you could also ask, why should this work at all, right? So imagine you have your training data, which consists of like one single training example. So you have the training example cat, and the plural form of cat is cats. And you train a model on that, so maybe an encoder-decoder model, and it learns, okay, I can produce cats if I know cat and plural. And you give it the test data point, plural and dog. Does anyone know what this would probably produce? Dogs? Okay, so yeah, I hoped someone would say that. Because I'm pretty sure, so I don't know, maybe there are models that could do that, but I'm certain my model could not do that just because it doesn't know which character belongs to which character. And overall, in general, if you train something on that, I mean, you know because you know how the plural form works, but in general, there's no rule that's clearly recognizable. It could be like append any character, right? And the most likely thing that a model would learn would be, oh, my output is actually cats. So this is something that you don't really want to do. But now imagine you have the same training data. So you have this one thing that's cat and plural, you want to produce cats. And then you add a lot of Spanish training data. So for example, you have mano, you want to have manos for plural, you have dentista, dentistas. And of course this is simplified, but we just assume that English and Spanish both append an S for building the plural form. And then you train a model on that one, and you give it your test data, dog and plural. And now the model has seen a lot of examples where it was just appending an S, right? So now it's kind of likely that the model can actually produce the form dogs. Okay, so in order to see that this is kind of actually happening in languages, we have here a Spanish and a Portuguese verb. So es lavar is to wash. And this is the present indicative forms. So the first four forms are actually equal in Spanish and Portuguese. So for all those cases, you would actually be able to just train on the data from the other language and to still get the right result, probably like simplified. And the only ones where it would differ would be like the last two forms. Okay, so what did we do? So we used the same model effectively, but we changed our input representation. So instead of just having the characters and the subtags, we now added a language tag. So we basically give the model one embedding that encodes what the language is that it wants to produce. And this is our final representation. So this would be important for the cases, like for the red cases in the table. So it's if the ending or like whatever the change you need to do to produce the right form is the same in both languages, then it doesn't really matter on what you train. But in case there's a conflict, then you want the model at test time to be able to distinguish what it should actually do. So this is why you need this language tag. Okay, so
Can you clarify what this, when you say input representation is this, do you mean that it's like if you're concatenating a bunch of tokens together and feeding it through?
Yes.
Like it's okay, so you're in what you're not doing is you're not on every character that you're feeding in also reminding it this is the language you're working on. Or
No, we did not try that. So it's just one thing. So basically the idea was we started off with the source and target tags and like, okay, what else can we use, right? Yeah. So that's, yeah, so it's parallel to that. So each of those has its own embedding. So each subtag and the language tag, they all have like one vector. Okay, so yeah, this is an example for the input representation. And it's basically the same as before, but you have the language tag. And the output representation is hopefully still the same. And so this is effectively multitask training on all tag-to-tag combinations and additionally on all languages that you like give to the model. So we did an experiment on the Romance language family, and we considered Spanish to be a low resource like target language. So we just reduced the training data for Spanish like a lot. We used Portuguese, Catalan, Italian, and French as the high resource source languages. And then we added one unrelated baseline source language because we thought, like what we said before, that it should potentially only work for closely related languages. So what happens if the language is actually not related? And the amount of source language instances we used were always 12,000. And then we changed the amount of the low resource instances in order to see what happens at like different amounts. So the questions we wanted to answer here were: first, is transfer learning possible for morphology at all between languages? Then how much annotated data do we need for the low resource target language? And how closely related must the two languages be in order to achieve good results? So this is for the Romance language family, mainly because we had kind of a good idea which languages were related. So on the left side, there's the lexical similarity between the language and Spanish, because Spanish was the target language. So Portuguese should be closest, then Catalan, Italian, and French. And lexical similarity is kind of like the vocabulary overlap in the languages. So it's not necessarily morphology, but we kind of used it to approximate. Then the curves, on the x-axis, there's the number of samples we used for Spanish, and the accuracy on the y-axis. And so basically the blue line, the light blue line, would be for in case you only train a model on the Spanish data, this is what you would get. And then if you add Arabic, this is the brown line, you get like a little bit of improvement, and then you get more improvement for like French, Italian, Portuguese, and Catalan. And it's mostly like more or less in order of the lexical similarity. So what we kind of concluded from this was that the closer the language, the better.
This is not cumulative. Those are each separately.
Yes, they're each separate. So it's always pairs. So it's one model per Spanish and something else. Then we looked a bit at the errors. So, for example, there were missing accents. So in Spanish, there are a lot of times there are accents on the verbs, especially that don't appear in the other languages. Then sometimes the model applied the source language inflection rules instead of the target languages. And then this is the problem why, like here, basically Portuguese is not the highest, right? Even though it should be the closest. And we kind of thought this was probably because the data was sampled in a way that we had a lot of lemma overlap between Spanish and Portuguese. And in case you train the model with like on one lemma and that the certain target form should look a certain way, and then you give it the same input in the other language, like exactly the same input. The only thing that differs is like this one embedding. So in those cases, the model was like pretty much never able to actually produce the right form. It always produced the one it had seen during training. Then we did a second experiment, which was zero-shot and one-shot transfer, because we thought zero-shot is cool. And we again used Spanish as the low-resource target language and the high-resource source languages all the same. But then we took all the Spanish data and basically separated the tags into like one half, for which we sampled one training example, like a random one from our data, and we had the other half of tags for which we used no training data. And the results we got for this were basically like this. So for the one-shot, so those are the tags for which we had seen one example. If we trained only on Spanish, we got like 0% accuracy. With Arabic, we still get 0%, and then with French, we get 13. Italian, we get 23. With Catalan, we get 39. And with Portuguese, we get 44% accuracy. Then for the other half, where we had seen like no training data, we have still 0 and 0. And then we have like 2, 1, 8, and 14. So basically the takeaway is don't do that. It's like, it's not really, but at least it does something, so we can sell it. Okay, so that was the part about the cross-lingual. So now the question was, okay, again, if we have like not so much training data and we also don't have a related language, so what can we do in that case? And the next like thing you could think about would be you want to use unlabeled data, right? So usually you have like large amounts of text in a language. So how can you include this here in the training? And what we did was, okay, so we wanted to make use of the large unannotated corpora, and we basically defined an autoencoding auxiliary task. So and then we trained the model jointly on autoencoding and morphological reinflection. So basically the idea was, instead of just giving it the reinflection samples, we also gave it some that was basically, that had a special like indication that said just copy this word. And the question is, why should this help? So one reason would be that the decoder's language model can be trained on unlabeled data. So this doesn't necessarily mean that the generation part, that doesn't really use any tags. And it reduces the problem of overfitting. So imagine you have a really low resource setting. So you could be very unlucky and all your words start with a B. And then the model, it's like similar to cats, right? So the model would basically learn that each word it produces has to start with a B, which is not what you want. So when you train on anything, even if it doesn't have any morphological information, it could learn that it can start with whatever. And it also gives a strong prior to copy the input string. So this is useful because many times a large part of the word is just the same for inflected forms, like smiling and smiled. So then what did we use here? So we basically used the same model as before, the same output representation, and then here we basically substituted each time we used an unlabeled example, the morphological tags by one tag that said, you should do the autoencoding. So basically copy this word in the decoder part. So this is how it looks like. And here's an example for the reinflection. So you have the input tag, output tags, the form, and then if you do autoencoding, you basically have one embedding that tells you the task, then the input word, and produce the output word. So input word and output word here have always to be the same. We did an experiment on the task 3 data this time of the SigmaFont 2016 shared task. Yeah, so mainly my work was on this shared task, that's why all of that. And this was morphological reinflection, and no lemmas were given. And again, 8 languages, and we used 2 baselines. So again, the 2016 baseline, which we used in the last experiments, and then the 2017 baseline, which was new at the time. And this is so basically the original training set consisted of 12,000 examples. And we wanted a low resource setting, so we just reduced it to 3,000 training examples. And those are the results of the baseline. So the baseline is kind of okay for German, Russian, Spanish, bad for the others. Then the other baseline is kind of also bad. And so the general, like the encoder-decoder model would produce that. And if you add the unlabeled data, you get like a little bit of improvement. So this is again the same thing. So basically this idea is to be used for low resource settings. And this is not like an extreme low resource setting. So if you reduce this further and look at 300 training examples, then the baseline does like significantly worse. So the best is like close to 40%. And the other baseline is also kind of around there. The encoder-decoder model is better here in this case for most except for Navajo. And then if you add the unlabeled data, you actually get like visible improvements. Okay, so this kind of worked, and then we thought, okay, like, why should this work? And if this works a lot because of the copying part, why don't we just use random strings? So basically our idea was just throw away the corpus data, generate some random combination of characters and use that. And we tried this on the task 1 of the 2017 shared task because it included more languages. So those were 50 languages for morphological inflection. And yeah, so the baseline, again, the one from 2017. And here's the average over 1,000 training examples. So this is the baseline. This is the normal encoder-decoder model. This is adding corpus data. And then if you add random strings, you get this accuracy. So basically the difference between the corpus data and the random strings, like about 0.8%. So there's still some difference, but it's like really like very, very close. No, sure, it's great.
So this kind of multitask learning that you're doing is a little unconventional, right?
Mm-hmm.
Usually you would say pipe everything through to some shared representation, and then they sort of go off and be decoded for the final state, output different answers for each of the different tasks. But in your case, the output is, it's just changing the input representation, and then the output is actually still just a sequence of characters, and the only thing that's different is the loss function that's grading that. Or no, I guess it's just the girl whole truth that you're comparing with for supervision.
Yes, true.
But that's, anyway.
Yeah, it's a bit unconventional, but I mean, it's basically using, like, it's sharing all parameters, right? Not just a part, so.
Sharing more than this other.
Yeah, but you're right. Okay, so basically there was one more thing that we did, which is the last remaining task. So I talked a lot about inflection and about reinflection. I did not talk about paradigm completion. So now here we do paradigm completion. So this was basically you have given one or more forms from a paradigm, create all the missing forms. And here the question is, if we have like several forms given, how can we make use of multiple input forms per paradigm. So, okay, the first question you would want to ask yourself is, in which settings does this actually make sense? So how does the generation even depend on the choice of source form? And we kind of analyzed this and said, okay, there are different settings that you could have. For example, here, you have one case where all forms are equally important. So if you have the English verb to lift and you want to produce lifting, it's basically the same if you start from lift, lifts, or lifted. So it's always just appending ing or take something off and append ing. So it doesn't really matter. Then there's another setting where one form is more similar to the target form. So for example, the German verb treffen. So here you can have treffe, traf, triff. If you want to use trafen, it's potentially easier to start off with traf than from the other ones. Then there's another case where you actually need multiple forms. So in Spanish, for the verb poner, if you want to produce ponga, it's not enough to have any of those forms. So if you just have pongo, basically this verb, the infinitive form of this verb could be pongar, and then the form you want to produce wouldn't be ponga, it would be ponge. And the same for if you just have poner, then you don't know if it's irregular, so the form could basically just be pona. So here you need to make use of both of them. Then there's another case where the necessary information is not available at all, and we basically don't need to consider this because it's just if you want to produce vent from go, goes, and gun, then you basically lost. You cannot do that. So here we changed the model a little bit. So instead of using one encoder and one decoder, we used several encoders, depending on the number of source forms we had. And we concatenated the hidden states, and the attention was over all hidden states. So our intuition was that the model at each time step can basically decide itself which one is the best source form. So this is how the model would look like for two input forms. So basically the orange one would be encoding the first word, and the blue one would encode the second word. And the rest stays the same, and we use one attention going over all hidden states. Here's an input example. So encoder 1 would get, so the input form is the lemma, so it's poner, and you want to produce third person singular subjunctive present tense. And the second encoder would basically get the same output tag. So again, it's the third person singular subjunctive present tense, but the input form is different. So now the input form is pongo. And then we would hope that it produces ponga as the output form. So we did basically experiments on task 2, again of the 2016 shared task, so reinflection. And we had the original data set, which had one input, one output in 8 languages. And then we sampled we tried two things. So we tried 2 encoders and 4 encoders. And for the 2 encoders, we sampled 1 additional form from the Unimorph data. And for 4 encoders, we sampled 3 additional forms. And those are the results we got. So this would be the single source one. This is with 2 source forms, and this is with 4 source forms. So basically, the takeaway from this one would be that the model is able to make use of the additional information that you presented with different encoders. Okay, so to conclude, so basically the important points are that neural sequence-to-sequence models are actually pretty strong for the morphological generation tasks, so sequence-to-sequence in general. Multitask training can improve performance in low-resource settings. You can use data in related languages, which can help. And unlabeled data or random strings can be used for an autoencoding auxiliary task. And additional source forms can give valuable additional information for that. Okay, thanks. Does anyone have questions? Yes.
So for the last thing, did you just sample the additional languages randomly, or is there a notion of relatedness that influences how good results are?
No. So, what do you mean? Do you mean the multiple input forms, or? Well, it's always forms of the same paradigm, right? So it's not like random forms. So, for example, no. So if it's this one, basically Okay, so we took basically the complete paradigm, so the one on the right, and the original data contained one source form. And then we just sampled from the rest of those forms, like 1 or 3 additional ones that were not the target form, obviously. Otherwise, it's kind of like useless. Was that your question? Okay. Yeah.
Would you expect, so did you ever try to do both the random strings plus the actual corpus data? I mean, I wonder if, you know, when specializing, letting it know which task, the difference between those two tasks, is it possible that it would be able to learn something useful besides just the copying corpus stuff that would, I don't know, that would fall out if you had both of those tasks happening once? That's both random, yeah.
So we did not try. I would assume it can't improve over the corpus data.
Okay.
Because, I mean, there shouldn't be any additional information in the random strings.
Assuming you have enough corpus data, I guess because all it's learning is this, the copying of,
Yes.
Similar to that, where you said in the semi-supervised case that using random strings out, that was technically all authority copying. So the random provides a signal in the sense that it's trying on copying.
Yes. I mean, I assume, right? There's no real way to like really say that, but yes. Okay. Okay, then thanks everyone.